Hi, it's Mr. Benson here with the second of my videos. This is looking a little bit more at the model of the atom that we use, and I think this really underpins a lot of understanding of a lot of the other ideas that you need to be familiar with in chemistry. So it's maybe a little bit out of order compared to what you've done in some other classes, but I think this is a really good idea. I can see from the survey results that many of you have done several science electives already, so if that's you, you should be pretty comfortable with a lot of these ideas. If not, even if you're someone in Year 9 and this is possibly even your first science elective, I think this is a really good place to start because it helps to explain why a lot of things happen. So it's not just the case of me telling you why something is, but you can actually start to link the ideas together and understand it a bit. So going back to what you would have started to learn about in Year 8, we know that atoms are made of protons and neutrons, which are in the nucleus, and electrons, which are around the nucleus. Now, what we have, or what scientists have figured out about 100 years ago, or in fact a little bit more recently even than that, in the sort of 1930s, was when a lot of these final discoveries were made, is to understand a little bit more about particularly the structure of the electrons around the atom. And so we say that electrons are located in what we call shells. And the model that we're using, which is a simplified one, we have our shells sitting around the atom, a little bit like the layers on an onion. Now, as I mentioned before, this isn't to scale. The nucleus is very tiny and very dense. The rest of the atom is mostly empty space and is much bigger than the nucleus, and the electrons are relatively distant from the nucleus. So that's pretty much the model that we've got at the moment. Now we need to look at that in a little bit more detail. So I've talked about the idea that elements are substances containing all the same type of atom, and by that we mean ones that have the same number of protons, and if they do, they'll have the same chemical and physical properties. Now, the atomic number is the number of protons, and for some strange reason that has the symbol Z. Now, one thing we'll learn about a little bit separately from this is that we can have different numbers of neutrons in atoms, but they're still the same element. So, for example, all carbon atoms have 6 protons, but we can have a look at different carbon atoms with different numbers of neutrons in them. So this is the example of what we call isotopes of carbon. So they're all carbon because they all have an atomic number of 6, but they are different isotopes because they have a different mass number. Now, if I haven't explained mass number before, the number here is the number of the protons plus the neutrons. So this is telling you pretty much what the mass of the element of the atom is. So with carbon, they've all got 6 protons, so carbon 12 has 6 neutrons, whereas when we go over to carbon 13, it has 7 neutrons, and carbon 14 has 8 neutrons. Now, this is actually not important to chemistry at all, because chemistry is concerned with what happens to the electrons in an atom, but it is relevant to physics, where we're talking about radioactive decay, because what we find is that some isotopes of atoms are unstable, and they'll undergo radioactive decay to become a more stable atom. So in the case of carbon, carbon 14 is an unstable atom that undergoes radioactive decay. Now, the shell model, which was one of the really important discoveries about the electrons, showed us that the shells around the atoms contain different numbers of electrons, and as you move out from the nucleus, which means that the shells have more energy, they can contain more electrons, so they're bigger if you want to think about it. So the simplest way of thinking about this, which will work for us at the moment is that we have an inner shell, which is shell number 1. It can have a maximum of 2 electrons. Shell number 2 can have a maximum of 8. Shell number 3 can have a maximum of 18. And shell number 4 can have a maximum of 32. There is a shell number 5, but we're just not going to get to that one. In fact, we're really only going to be thinking about what's going on in the first 3. Now, like anything, things want to go to the lowest energy level. So when we drop something, it falls down to a low energy state. And electrons are much the same thing. They will always fill from the inside out. So they'll go into the innermost shell first, they'll fill that up with 2 electrons, and then they'll go into the next shell. So we can start to think about the electron configuration of an atom. So with carbon here, we've got a total of 6 electrons, so we put 2 on our inner shell, and then there'll be 4 remaining on our outer shell. Now that's really important, but it won't make sense just quite yet. So just to show you a diagram of that, again, we pop 2 electrons on our inner shell, and then the remaining 4 we put on our outer shell. So I'd like you to have a go at drawing some of these. So you need to look on your periodic table. Now there was one in the previous video I showed you. You could Google them, or in the Jack Plus book you'll almost certainly find one. And I would like you to follow the steps that I did. So you've got to think about the number of electrons that can fit in the shell, and then draw the electron configuration for them. So I'd like you to have a go at drawing one of these, some of these diagrams for yourselves, and I'll just quickly remind you how to do it. So I'm going to choose fluorine from this list. Now you'll need to look on the periodic table to find out the atomic number of the substance, and fluorine has an atomic number of 9. Now the mass number is not important, because the only number that tells us about the number of electrons is the atomic number. Now I may not have explained this previously, but the atomic number is telling you that there are 9 protons, which have a positive charge. So we've got 9 positive charges in the nucleus of the atom, and so we have 9 electrons which have negative charges, so 9 negative charges, and that balances the charge for the whole atom and gives us a neutral atom. So when we're drawing the diagram, we've got 9 electrons to play with. So I draw a little dot to represent the nucleus, because in chemistry we pretty much don't care about the nucleus. And then I'm going to draw 2 dots to represent the first 2 electrons in the inner shell. Then what we've got to think about is how many are left over, and 9 minus 2 means we've got 7 electrons left over. So apologies for the terrible circles, but they don't have to be beautiful. Okay, so I'm going to draw my remaining 7 electrons, 1, 2, 3, 4, 5, 6, 7, around the shell there, and that's it. I've now drawn the electron shell diagram for fluorine. Now what we can start to do then is to look for some patterns in the electron shell diagrams, and this is an activity that I'd like you to do. I'd like you to draw the electron shell diagrams for the first 20 elements, and we're going to write some, I'll give you some information about the properties of these substances, and then you'll start to see that there are some patterns that we're noticing. And even when we just look at the periodic table, we're going to notice some patterns in relation to the electron shell diagrams that you're drawing and the periodic table itself. So you'll need to find a periodic table for this. I suggest you draw out a table on a page so you've got enough room to actually draw all the shell diagrams, and proceed to draw them for the first 20 elements. Now you may have already done them from the previous page on the slide, so you can just copy those ones over. Now we'll come back to this in another in my next video, and we'll actually discuss what these patterns are.